Okay, Dr. D here again. This is our chapter 14 video, chemical equilibrium. And what equilibrium is the point at which the forward rate equals the reverse rate, not the rate constant, the actual rate. It's a dynamic system. Reactants are going on to form products. Products are going on to form reactants, just happening at the same rate. So we see no changes in concentration once you reach equilibrium. So if we were to graph, say, concentration versus time, we would see for the reactants something along like this, and maybe for the products something like this, right? And you reach a point at which maybe right here there's no change in that concentration. That would be equilibrium. The rates then, of course, would look like this. If we were to graph the rates versus time, the rate of the forward reaction will be decreasing. That's the forward reaction. And the rate of the reverse reaction would be increasing, starting at 0, assuming we have no product. That's the reverse reaction. The rates become equal. Now, it's important to realize that you can come at equilibrium from any point. You don't have to start with all reactants. And if for a particular reaction, if equilibrium is known, that will be the same all the time. Okay, and that is the amount of reactants and products. So I can start with all reactants, or I can start with all products, or I can start with some mixture of reactants and products. Ultimately, the ratio of those amounts will be the same. Not the amounts, because you can change the amounts and you can have less of reactants and not have the same concentrations in the end, of course. But the ratios, as we'll see as we define what a rate constant is, we'll see that those ratios will be the same regardless of how you approach equilibrium. So here's a particular reaction that we've studied. And here are the rate laws, and we've deduced this from experimental data. So at equilibrium, since the two rates are equal, we can set them equal to each other at equilibrium. And if you rearrange this, I guess, you'll notice that we can get kind of like the products, right? These are the products over the reactants is equal to this ratio of rate constants. And this ratio of rate constants just is given a new designation, like capital K, and it's just a new constant. It's a ratio of those two constants. So that is what the rate constant is equal to. It's going to be equal to the ratio of those two rate constants, but it's also going to equal the products over the reactants. And we'll explore that a little bit more in a bit. Now, it's important to realize that many reactions fail to go to completion. And when we say completion, we mean all the reactants converted to all products. That's actually fairly rare. Spontaneity, if you will, is not yes or no. It's either spontaneous or it's not spontaneous. That's not the case. If there's more reactants than products, then we say it's product favored. Okay? If there's more reactants than products, and I say that backwards, if there's more products than the reactants, it's product favored, obviously. If there's more reactants than products, it's reactant favored. There's no definitive, definition. It's just we say spontaneous means that it's product favored, and we're going to form an appreciable amount of products. We're going to have a lot more products than we do reactants when the reaction is done. That's all spontaneity means. Okay? It's not hit or miss, okay? It isn't definitive. It just means you're going to form a decent amount of products, okay? So now, when you look at what an equilibrium constant actually is, it turns out that you can write it from a stoichiometric equation. And to try to explain this to you is just beyond this course, to be honest with you. It's even beyond, to a large extent, undergraduate chemistry. You might get a treatment of in physical chemistry, but it's a very difficult concept. And it has to be derived. And it's one of those things you can see debated online in different forums and Quora and stuff like that. Ultimately, I like to say it's like you just got to do the math to convince yourself that ultimately a reaction at equilibrium does not depend on the mechanistic steps and the coefficients in the rate laws and all of that. So even though it's equal to the ratio of these rate constants at equilibrium, it's not dependent on the rates, okay? Because the rates are equal. It's not dependent on all the mechanisms involved, the multiple steps that might be involved with intermediates and the different rate constants and the orders of the reaction. Okay, so you can literally understand that from a thermodynamic standpoint, the coefficients of a stoichiometric reaction are important because K is going to be related, we'll see this, to free energy, the energy of the system. And the number of bonds being broken and formed is critical to that. And that is dependent on the stoichiometric coefficients because you have a 2 there. That means 2 molecules have to be broken down rather than 1. So with that, let's just accept the fact that this is the way it is, okay? You can write it directly from a stoichiometric coefficient. It's just the concentrations, and this is moles per liter always, raised to stoichiometric coefficients. An equilibrium constant is much more complicated than this. It derives literally from activities, not from concentrations. And activity is something you will be exposed to at some point in your advanced chemistry courses. And these are actually ratios of activities. But for ideal systems, these can be estimated from concentrations appropriately. So you see the equilibrium constant is much more complicated than is shown by this and how it's derived. But all we need to understand is that these brackets always mean concentrations. They're moles per liter. You simply write the products over the reactants raised to the stoichiometric coefficients, and that equilibrium constants are unitless. Okay? They're always unitless. If you find something using units, that's incorrect. Okay? And you can also write it for pressures, and that's all. You do it the same way. It's just going to be in pressures. Now, there is an equation that relates these two. I won't ask you something like that on an exam or even a quiz. I just want you to be aware of it. I might have asked you it in smart work or the back of the book or something like that, or one of the exercises within the chapter, and that's okay. I just want you to be aware of it, that if you calculate a Kp to get a Kc, there's an equation that will allow you to convert those because one's in pressure and the other one's in moles per liter. So how do we interpret these K values? What do they mean to us? Well, it's pretty straightforward because it is a ratio of products to reactants that a very large K favors the formation of products. So this one is huge, just to make a point, 10 to the 81. Now you could say that theoretically we have 3 times 10 to the 81 times more product than we do reactants, but keep in mind this equilibrium constant is going to have a square here, and it's going to have, this times this. So it's not exactly that straightforward to say there's 3 times 10 to the 81 times more product than reactants because we got squares and multiplications. But in general, we think we have a huge amount of product here formed compared to reactant. And in this one is an incredibly small one. Okay? Carbon dioxide just doesn't break down to form CO and O2. Okay? To any appreciable extent. It's not spontaneous. This would be spontaneous. This would be non-spontaneous. It doesn't mean there's going to be no carbon monoxide or oxygen in the system. It just means equilibrium lies way towards the reactant side. In this one, equilibrium lies way towards the product side. And here's one in which we're still going to have appreciable reactant left. So we might not say this is, a real spontaneous reaction. We clearly can see that we have more product than reactant because the Kc value is 24. So effectively we have 24 times more product than the reactant if you look at it simply like that, but it's not a huge equilibrium constant. So we might still say that this is spontaneous. It really is somewhat qualitative how people treat this. There's no definitive line that says, okay, when Kc equals this number, we say it's spontaneous. So when you write equilibrium constants then, it's pretty straightforward. Products over reactants. However, there's something we need to consider. First, this one here, right, should be pretty obvious to you. Products over reactants raised to the stoichiometric coefficients. But this one looks a little odd because this is missing. Turns out that pure solids and pure liquids, if you have an L like that, do not show up in equilibrium constants. And that's because their concentration never changes. And you think about that, it really is the case where a solid, if you think about a solid reacting in a beaker, this one's in air, but you could just think about a beaker of water and a solid in the corner here reacting. It's part of the reaction. But the concentration of that solid never changes. You know why? Because it's not dissolved in the water. So its concentration is simply its density, because concentration is grams per unit, is mass per unit volume, and that is simply a density. The density of this, S8, if it's S8, never changes because that's just the element. That's sulfur. It never changes. And the density of a pure liquid doesn't change. So effectively, its molarity never changes because it's equated to density. So that's why they don't show up in equilibrium expressions, where gases and anything dissolved in solution are going to change their concentration over the course of the reaction, and therefore the concentration term needs to be in the equilibrium expression. So just be aware for solids and liquids. And because they're not in the equilibrium constant expression, when we talk about stresses that are applied to a system in equilibrium and how those stresses cause the equilibrium to adjust, or cause the system to adjust and reestablish equilibrium, adding a pure solid or a pure liquid will not change that system, and it will not have to adjust to that stress. And that'll make more sense when we get to that section. So, one thing your book spends some time on, it's something I think is, is straightforward enough that I'm going to do it on the video and really not spend much time otherwise with it. And that is how the K for one reaction can relate to another. So clearly, if we have a reaction like A plus B goes to 2C, there's my equilibrium constant. The reverse reaction is just 2C goes to A plus B. So the K of the reverse reaction, they're just inversely related. So what the value of this is, if you have an equilibrium constant for a particular reaction, you don't have to worry about measuring the equilibrium constant for a related reaction if it can be derived from the initial reaction. So if it's just the reverse reaction, then obviously you know what it is. It's just the inverse of it. If you take a stoichiometric reaction and multiply it by a coefficient, let's say you have an equilibrium constant for a reaction like this, but you're actually working with a system like this, well, you know the equilibrium constant. You can rewrite it, of course. This is why I kind of think this section is kind of mundane to spend a lot of time on, is that you can just simply write the equilibrium constant for the new reaction, and you'll get this. Or you can take the K1 and just raise it to the half power, and then you have the value. Okay, so in this case, if experimentally you weren't able to measure these, of course, then it'd be easy for you to know what your K is. So that's the advantage of this, but it's not something that it's critical to Gen Chem 1. This can be useful if you have a series of reactions. Let's say you can't measure the concentrations for a particular reaction. Maybe one of these concentrations is tough to measure or something. But if you know the equilibrium constant for these two reactions here, and this adds up, if you look at this now, the 2 and O cancel out, N2 comes down O2, and the 2 and O2. Those two cancel out, and so the equilibrium constant really winds up just being the product of those two. And we can see that here, that this is going to cancel out, and this is going to cancel out the same way. So you wind up with an equilibrium constant that is equal to this, but, if you will, it gives you an option to consider how to get to that equilibrium constant. That's all this whole section is, and there's a bunch of it in your book. Okay, now a very important concept is the reaction quotient. And the reaction quotient is exactly the same as the equilibrium constant mathematically. It is just products over reactants raised to the stoichiometric coefficients, but it's calculated when you're not at equilibrium. So you're going to calculate the concentrations of, let's say here's our reaction. You're going to calculate the concentration of those raised to the powers, and that will equal Q. It's going to not be at equilibrium. So Q just equals K at equilibrium. But the power of this is to figure out, you can compare Q to K, because that'll tell you where you lie relative to equilibrium. So for instance, this is a nice graph. It shows you if Q is less than K, which is right here, then the system needs to produce more product. Because remember what it is. It's products over reactants. So if it's less than K, that means we need to increase the numerator, which is more products, and decrease the denominator. So you're going to move towards equilibrium. If you have Q greater than K, you're in this scenario here, and effectively you're going to go in the opposite direction. So it becomes really important in understanding that, because we tend to think about reactions moving in the forward direction. When we say spontaneous, we mean if I take reactants and put them together, do I form products appreciably? That's what it means when to say it's spontaneous. But when we talked about delta G and delta G naught, which is coming up, we'll see how that relates to where we are in the reaction profile and whether or not it's going to be spontaneous in the forward direction. Because we could be anywhere in the reaction profile. So now we're exploring a little bit more of not just starting with all reactants all the time, because that is fine in the lab, and that's the way you do it in the lab. But what if you're studying a reaction in soil, or you're studying a reaction in the human body where there's already some product formed, or you're studying a reaction in a lake? So these become a much more practical approach to understand equilibrium from that perspective. Just a couple little terms: homogeneous and heterogeneous equilibria. Homogeneous means involve reactants and products all in the same phases, so these are all gases. Heterogeneous, well, we can have some that are solid, some are gases. Now, when you have a heterogeneous equilibria, you got to realize that, hey, those pure solids don't actually show up in the equilibrium constant expression. So you see, from this, we would write this, but the actual Kc winds up just being this, because the pure solids are not included. So it winds up just being CO2. Okay? And now, when we get to Le Chatelier's principle, a system in equilibrium responds to a stress in such a way that it relieves that stress. And we're going to spend a lot of time on this in class. And this is something I wish was almost introduced earlier in the textbook. But the system responds to reestablish equilibrium. Factors that will change the relative rates of forward and reverse reactions, or change the value of Q compared to K, will cause a shift in the position of equilibrium. So for, let's say we have A goes to B, and this is the way we write arrows now for equilibrium systems to show that it's forward and reverse. This system's at equilibrium. Let's say now, you can imagine a lake or something in your body. The system's in equilibrium, then all of a sudden more A is pumped in. What happens? Well, now what has happened? Q is less than K, right? We have a higher concentration of reactants. How does the system respond? It responds by producing more B. K will be reestablished, and K initial will equal K final, because the equilibrium constant is always the same, because it's a ratio. Will we have more products now and more reactants than we had before I added that A? Yes, we will, of course. But the ratio will be the same. That's the key. The equilibrium constant is always the same. It only changes with temperature. It doesn't change if I add more concentrations of something. It just reestablishes. That's the stress. And, however, in this type of system, if I were to add more S, more of a solid, like calcium oxide, the equilibrium does not change. It's not a stress, because that's not in the system. It's just a constant concentration anyway. So adding more doesn't matter. You have plenty left there because it's not in the system. It's not dissolved in the gas phase. So adding those do not create stresses. And we'll deal with these stresses in many ways in class. We'll look at temperature, we'll look at gases, but same thing, if I remove B from this system, the system's going to respond by producing more B. It's always going to respond by consuming something that's been added, or removing something, consuming something that's been added, so removing it, or replacing something that's been removed by producing more of it. Quick note on catalysts. You know what catalysts are. They speed up the rate of the reaction. Here we see a catalyzed reaction, lowering the energy of activation. What I want to stress here is there's no change in K or the position of equilibrium. K is not affected by the catalyst because K is not dependent on rates and mechanisms or any of that. Remember, it's just the point at which the forward and reverse rates are equal. And those forward and reverse rates are composites rates of the entire mechanistic system with all the orders built in and all of that. And that's what allows us to write it directly from stoichiometric coefficients, because at equilibrium, all that matters is how quickly the reactants are forming products and products are forming reactants. They're the same, but that's all that matters, not the mechanism and not the orders and any of that. So equilibrium stays the same with a catalyst. And one of the most important equations in Gen Chem 1, I believe, that brings everything together, Gen Chem 2, is this equation right here. And it's disturbing to me. It must have been left out accidentally, but it is not in the list of equations at the back of your textbook, because the back of your textbook does have, in the summary section, they have all the important equations. And this one's not listed for some reason. So go figure. But anyway, it's really important. So what this tells us, it relates delta G to Q, which is the amount of products and reactants are formed. So you can imagine, remember these profiles we drew, where this is G versus reaction progress, or time, if you will. And you can see how where Q is the amount ratio of products to reactants, that Q's changing and G's going to change as Q changes, right? Delta G naught doesn't change. It's just based on the free energy of formation of reactants and products. That's constant, but delta G, so Q is going to be changing. And here's equilibrium, right? So at equilibrium, Q equals K, and delta G equals 0. So you wind up with delta G naught equals negative RT ln of K at equilibrium. And you can see that delta G naught is related to K because delta G naught is an indication of spontaneity and how much product forms, and that's what K is also. Okay? So delta G naught does tell you where equilibrium lies if you were to start with all reactants. But what if I'm right here? In my reaction profile, I've got some reactant and some product, and I'm actually to the right of equilibrium. Delta G naught doesn't tell me anything about that. Delta G does. Delta G would say this is not spontaneous because you're not going to form any more product. You're actually going to go back and form more reactant to get to equilibrium. So G will tell us about true spontaneity of any point in a reaction profile. Delta G naught really only tells you, hey, if I start with all reactants, can I expect to get product? And that's related to K. So we'll spend time on that in class. And this figure, I just end with this because you need to, delve into this figure, spend some time with it, because it's a really good figure that brings together free energy G, G naught, and the extent of product formation. Because here you got your K values. And that's really important to bring this all together. That's the power of this chapter, if you will, to bring together, equilibrium constants with free energy. And that concludes the video.